Okay, hello, Chapter 3. Chapter 3, Section 3.4, which deals with both exponential and logarithmic equations. So what are we trying to do with this section? We're going to solve simple exponential and logarithmic equations. We're going to solve a little bit more complicated equations of both, and then we might get into modeling some real life problems. Okay, so let's get into it. So there's two strategies for solving exponential or logarithmic equations. The first one is based on that one-to-one property where you compare them, and if it's the same base, you can just take away the base and leave the exponents. And that's pretty much used to solve the simple case. And the next one is based on the inverse properties. So I will show you for a greater than 0 and non-1, so not 1, all these properties are true for every x and y in which log of x and log of y base a are defined. Okay, so one-to-one is this. So this is just restating what we said before. We said this already, and you've seen this already, but hey, just to be thorough, if you have two exponential functions that are the same base and they're equal to each other and they may or may not have different exponents, because of the same base, you can just you can essentially just stop considering the base part and consider only the exponents. So if you have two same base exponential functions, you can drop the base and just compare exponents, set them equal to each other. And also, if you have two logarithmic functions of the same base that are equal to each other, and no other factors or terms, of course, on either side of the equation, you can just drop the logs and compare the arguments. So if and only if x is equal to y. The reverse, this also works in the reverse or the converse, the other way. So if you have two quantities that are equal to each other, let's say one of them is x and the other is y, you can kind of like take the log of both sides. That's kind of one way to think about it. If you take the log of both sides, then you'll have this log of base a of x is equal to log base a of y. And then you can also raise both of them to the same base. So, okay. And then also inverse properties. So if you have base a to the power, so the power log base a of x, so where the exponent itself is a logarithm, but they have the same base, these cancel out and you're left with the argument of the exponent x, of the exponent log, okay, which is x. Okay, and then the other inverse is if you take log of base a of the argument a, but now the argument is also, so the argument matches the base here, but now you have an exponent attached to it, you know, this cancels out because they're the same, the argument here and the base here are the same. You're left with whatever the exponent of this whole thing on the left-hand side is. So let's see some examples of the properties, okay? So let's suppose you have 2 to the x is equal to 32. Well, I can rewrite 32 as 2 to the 5th power, and then I can compare exponents, and there I've solved it, x is equal to 5. If you have ln of x minus ln of 3 is equal to 0, you can add both sides, ln of 3 to both sides, and you get this equality here. And if I have the equality, then just by using the one-to-one property, I can say that x is equal to 3. Okay, let's try another one. 1/3 to the x power is equal to 9. Well, I can rewrite both sides of this equation in terms of 3. So I can write 1/3 as 3 to the negative 1, or the whole 1/3 to the x power as 3 to the negative x power. And 9 I can rewrite as 3 squared. So now that they have the same base, I can just let the exponents equal to each other. So I get negative x is equal to 2. And then I simplify, so x is equal to negative 2, and that's using the one-to-one property. What if I have e to the x is equal to 7, and I want to simplify that? Well, if I take the ln of both sides, then this ln of e will cancel out, and I get on the left-hand side, and I just get x is equal to ln of 7. It also is worth mentioning that if I take this e to the x equals 7, and I rewrite this as an ln, I will get my x. Okay, so that's another thing to consider. You can also solve it that way. If I have ln of x to the negative 3 power, I can raise both sides of this equation to the power of e, and I get e to the ln of x, which will just give me x, and e to the negative 3, and that's the answer. Okay, so here log of x is equal to negative 1. I can raise the left-hand side and the right-hand side to base 10. So basically I'm taking 10 and I'm using the left-hand side of f as the exponent and the right-hand side of this f as the exponent. So 10 to the log of x power and 10 to the negative 1 power. 10 to the log of x will just give me x, and then 10 to the negative 1 is, of course, 1 over 10. Okay, and then finally, log base 3x is equal to 4. If I raise both sides to have the base 3, so the bases here will match on the left-hand side, and I'm left with x, which is what I wanted. And on the right-hand side, I have 3 to the power 4, which is 81. Again, you could have also written this into exponential form, so you would have said, okay, 3 is the base, raised to the power 4, that equals x, and you would get the same answer. Okay, so what are some strategies that we used to solve these examples? So what we did was we rewrote the original equation in a form that allows us to use the one-to-one properties. So what does that mean? We basically put the equation in a way where it's just 3 to the power of something on one side and 3 to the power of a different thing on the right-hand side, and we compared the exponents. Okay, and the same thing for logs. Okay, another thing we could do is we rewrite an exponential equation in logarithmic form and we apply inverse property, or we rewrote a logarithmic equation in exponential form and we applied the inverse property. Okay, so let's continue. So solving exponential equations. So let's solve each equation and approximate the results to 3 decimal places if necessary. And here you have e to the negative x squared, and you have here e to the negative 3x minus 4. And then you have 3 times the quantity 2x is equal to 42. So for the first one, we have e to the negative x squared is equal to e to the negative 3x minus 4. That's the original. So then by one-to-one property, the e's cancel out and we get negative x squared is equal to negative 3x minus 4. Solve this for 0, so I can add this to both sides, x squared to both sides. I get x squared minus 3x minus 4 is equal to 0. Then I can factor this. And then I get 2 solutions. The first factor is equal to 0, gives me x is equal to negative 1. The second factor equal to 0 gives me x equals to positive 4. So then check in the original, and you can verify that it's correct. Okay, so for the b, let's write the original equation, and then we need to get it to where you have one exponent on the side, right? So let's divide both sides by 3. Okay, so that gives us 2 to the x is equal to 14. If we take the log of base 2 to both sides, we get that x is equal to log base 2 of 14. But in order to plug this into our calculator, we need to write this as a change of base formula. So we could use ln, we could use common log, doesn't matter, we'll still get the same answer. So x is equal to, and then you have ln of 14 over ln of 2, and that gives us 3.807, and you can check that in the original equation to see if it's correct. Okay, now let's do an example of solving logarithmic equations. So to solve a logarithmic equation, you can write it in exponential form. So here, we could go, if you have ln of x is equal to 3, you can exponentiate each side. Well, that's a nicer way to put it, exponentiate. And then because of properties of logs, that gives you x is equal to e to the 3rd power. Now, the only thing I can also say about this is you could have just gone from logarithmic to exponential, and if you recall last semester I taught you guys how to do this. So if you remember how to do that and it's easier for you, go ahead and do that. So just another way to do it is to do this exponentiating each side. All right, so let's say here your original equation is ln of x is equal to 2. If we exponentiate each side, you get e to the ln of x is equal to e squared, and that gives you x, which is equals to e squared. And then here, let's say you have log base 3 of the quantity 5x minus 1 is equal to log base 3 of x plus 7. So then by one-to-one property, you can just let the arguments equal each other. So you get 5x minus 1 is equal to x plus 7. And then solving for x, you can get 2. Okay, and then finally, let's see this one. We have here log of base 6 of 3x plus 14 minus log of base 6 of 5 is equal to log base 6 of 2x. So using the property of logarithms, I can condense this left-hand side to be log base 6 of the quotient 3x plus 14 over 5. And on the right-hand side, I get log base 6 of 2x. So now because they're the same, the log base 6 I can cancel out by one-to-one property, and then I get 3x plus 14 over 5 is equal to 2x. And then if I multiply both sides by 5, I get rid of the denominator on the left-hand side, giving me 3x plus 14, and on the right-hand side is 10x. And then from here, subtract 3x from both sides. 14 will equal 7x, and divide by 7, and you get x is equal to 2. So that's it for 3.4, and I'm very excited. That's the end of chapter 3, so it is really exciting. So I will see you guys on the next video. Happy studying.